very good morning and welcome to this course on the foundations of continuum mechanics. Today, we will be talking about principal values and directions. So let's get started. So the topics we will be discussing today include a discussion on linear transformation. We will talk about the meaning of principal directions and principal values, and then we will discuss the characteristic equation and the various cases when solving the equation. So let us start with the concept of linear transform. So let's say sigma ij is a second order tensor and we write Vi as sigma ij uj. So what we are doing is that we are taking or going from a vector u to a vector v by multiplying u with a second order tensor sigma. So this is called a linear transform. And what are we transforming? We are transforming the vector u into a transformed vector v. So let's write it in the matrix form and have a look. So this is the matrix form of the equation, and if we were to expand this, it will be written like this. So from these three equations, we can see that each component of the transformed vector v is a linear combination of the three components of the initial vector u, and the weights or the coefficients for the transform are nothing but the components of the tensor sigma. So this is why this is called a linear transform. Components of v are linear combination of the components of u. Now I have not told you why we are having a discussion on the idea of linear transformation, but it will become clear in a moment. So what is clear as of now is that sigma ij, that is the second order tensor we're talking about, is important for the discussion here. We will make some assumptions to sigma, that is, sigma for the today's discussion is real valued, that is, all the components of sigma are real numbers, not imaginary numbers, which makes sense for us because in this course we will be dealing with real numbers. And it is also symmetric. Now this may seem like a strict assumption, but it is not, because the kind of second order tensors we deal with in continuum mechanics, as we will see later in the course, are usually symmetric. So it makes sense to have a discussion about symmetric matrices or symmetric second order tensors such as sigma in this case. So we will underline these two words because these assumptions are important. So symmetricity means that sigma ij equals sigma ji. Now sigma usually is a physical quantity or a geometrical quantity, and it varies as a function of space. So what I mean to say is that if you have a point P, let's say somewhere here in my XYZ space, then the value of sigma will change as I move my point P. So when I'm having the discussion, I'm always having a discussion for sigma at a given point in space. In addition, we'll also assume that the vector u we talked about in the linear transform, it is a unit vector. So we'll write it as Vi equals sigma ij nj, where n hat is a unit vector. So these are some assumptions we are making to start the discussion on principal values and directions today. So I will box this equation because this is the equation of interest today. Now let us talk about why we are talking about a linear transformation. So we will do an experiment. That experiment involves multiplying sigma with an n. So let's say you have a direction n, let's call this n hat, and you have sigma, which is basically comprised of 9 components defined at a given point in space. So if I define sigma at a given point in space, it has 9 components, and I'm multiplying sigma with an n, and that results in a vector v. So let's say the vector v looks something like this. So what the experiment involves is that we take some n hat, we multiply sigma with an n hat to get a v, and now we play around with this n hat. So what I mean is I move around my n hat in the experiments and I tabulate all the v vectors I get as a result. So let's write this experiment. Now in most cases we see that the vector v will point in some direction that is not the same as n hat. And why should it be? Because v is obtained by multiplying sigma with n hat, and sigma of course is arbitrary in a sense that we did not choose a particular kind of sigma. It is simply depending on the physical situation at the point P. But what we notice, the interesting fact here is that for some special n hats, what happens is that the vector v points in the same direction as n hat. In general, v is in a different direction than n hat, but there are some special n hats for which vector v will be in the same direction as n hat. Another way to say that is the vector v is a scalar multiple of the vector n hat. Now lambda can be less than 1 or more than 1. That is, the vector v can be smaller than unity in magnitude or greater than unity. In fact, lambda can be negative as well. That is, the vector v is in the opposite direction to n hat. In fact, these special n hat vectors are called the eigen directions. And these eigendirections, that is these n hats for which the vector v, which is obtained by multiplying sigma with n hat, points in the same direction as n hat. So these eigendirections are common in continuum mechanics or mathematics or engineering in general. In fact, these eigendirections have a very special meaning in most cases in engineering. So they have a very special physical meaning depending on the subject. And we'll discuss this meaning in the context of continuum mechanics later in the course when we talk about stresses. For today, we will stay with the mathematics. And given that these directions are special, physically speaking, so these directions are also called principal directions. Let me ask you a question. Are these principal directions dependent on the second order tensor sigma ij? And the answer is yes, of course. Because these principal directions were obtained by multiplying sigma with n hat and finding the vector v to be in the same direction as n hat. Of course, if I change my sigma, the linear transformation changes, and so does the n hat or the special n hats known as the principal directions also change. Now, since these directions are important, I would want to know these directions. Now, the question is, how do we find these directions for a given sigma? Of course, I cannot perform infinite number of experiments. That is, I cannot use the brute force method where I guess an n hat and try to find a v vector and keep doing that until I find the principal directions. That will result in an infinite amount of time. So we need an elegant method to find the n hat or these special n hats or the principal directions. So let us proceed with the process of finding special n hats, that is the principal directions. So we started with Vi equals sigma ij nj, which was the linear transformation. But for these special situations, this Vi is equal to lambda times Ni. So this is the equation that is important. And if we can solve this equation, of course, sigma ij is known. If we can solve this equation for n hats, we get the principal directions. But along with n hats, we also have a lambda here. In fact, this lambda also has a special name. It is called the principal values or eigenvalues of sigma ij. So in this situation, lambdas are principal values of sigma ij and n hats are principal directions of sigma ij. It is important to mention that they are properties of sigma ij because otherwise it has no meaning. So this equation, that is sigma ij nj equals lambda times ni, is the equation we are trying to solve now. So I can write the right hand side as lambda times delta ij times nj. So that's somehow using the substitution property of delta in opposite. And why did I do that? Because I wanted to have nj as common, and then I'll move everything on the left hand side. So this becomes sigma ij minus lambda times delta ij times nj equals 0. You may have seen this equation in linear algebra. In fact, let me write the symbolic notation as well, which may seem more familiar. And this equation is a null space problem. This equation for a non-zero nj's only has a solution if this matrix is singular. And mathematically, singularity can be represented using a determinant. So we can say the determinant of sigma ij minus lambda times delta ij is equal to 0. Let us expand this determinant. So we can write sigma 1 minus lambda, sigma 1 sigma 1 So only the diagonal terms will have a minus lambda because the lambda is multiplied to identity. This determinant is 0. And remember, sigmas are known. We're trying to find the eigenvalues and directions of sigma. So sigma definitely is a known value, but lambda is not known. So from this equation, we are trying to find the values of lambda. So you can see that if you expand this, you will get a cubic equation in lambda. This cubic equation in lambda is called the characteristic equation. It is very important because this equation, when solved, gives us the values for the three eigenvalues, that is lambda 1, lambda 2 and lambda 3, which are what we need to find. Now, of course, the coefficients of this equation will be in terms of sigmas. And I have written a 1 sigma, 2 sigma and 3 sigma as the coefficients. I need to expand that and tell you what they are. So the first coefficient, 1 sigma, is in fact called the first invariant of sigma. And you may remember this from one of the problems we solved. This is sigma ii, which is sigma 1 1 plus sigma 2 2 plus sigma 3 3, which is also called the trace of the sigma tensor. Now, this is very interesting that the invariant or the invariants we talked about earlier are appearing in this characteristic equation as coefficients. Let's talk about the second coefficient, which, as you may have guessed, is called the second invariant of sigma. And it's represented as half sigma ii sigma jj minus sigma ij sigma ji. Now, this coefficient in the characteristic equation is also an invariant. And the third coefficient, also known as the third invariant of sigma, is simply the determinant of sigma, which in the initial notation can be written as epsilon ijk sigma 1i sigma 2j sigma 3k. So these are important quantities, and it is worth calculating their values for any sigma that you have. And as we discussed and we showed that sigma ii is an invariant, we had shown that. So that means sigma ii sigma jj, they are also invariant, and we had shown that sigma ij is an invariant as an exercise as well. But in this case you have sigma ij times sigma ji. But remember, sigma is symmetric, so this is basically the same as sigma ij sigma ij, which has been shown to be invariant. So the second invariant is also, we have shown that as an invariant through various previous exercises. But we have not shown that the determinant of sigma is an invariant. So this will be discussed as one of the problems later this week. But our job here is not to show that these quantities are invariant. They can be shown later. We can just accept the fact that they are. But what's interesting today is to know that they appear as coefficients in the characteristic equation. And you can expand and check. You can expand this determinant and it will have lots of sigmas in their combinations coming as coefficients, and you can compare that with these 1 sigma, 2 sigma and 3 sigma, and the coefficients will be the same. Now let's understand the importance of the fact that these coefficients in the characteristic equation are invariants. Let's take a situation where you have a coordinate axis O, x1, x2 and x3, and we perform a transformation, a rotational transformation, so that we get a primed coordinate system, that's O, x1 prime, x2 prime and x3 prime. So sigma was defined in the base coordinate system. So sigma ij, the tensor, because you had 9 components, so the 9 components were defined in O, x1, x2, x3. And when you transform from the base to the prime coordinate system, then you will get a sigma prime ij, that is 9 new components in O, x1 prime, x2 prime and x3 prime. So let us say we were working in the prime coordinate system. Again, our initial choice of the coordinate system was quite arbitrary. we just chose a base coordinate system. But let us say we had rotated our room and we were initially working in the red coordinate system. Now sigma being a tensor, and if we had measured the 9 components of sigma, they would be what we are getting in sigma prime because we are working in the prime coordinate system. So let us say if we were working in the primed coordinate system and we tried to find the eigenvalues of sigma prime, what would we get? So we would write a characteristic equation, and that equation is given as lambda cube minus 1 sigma prime times lambda squared plus 2 sigma prime times lambda minus 3 sigma prime equals 0. So this is if analyzing in O x1 prime, x2 prime, x3 prime. But we know that these invariants do not depend on the coordinate system in terms of rotations. So what that means is that I sigma prime is the same as I sigma. Sorry, these were lambda squared and lambda. 2 sigma prime is the same as 2 sigma, and 3 sigma prime is the same as 3 sigma. So the eigenvalues, the 3 lambdas I get in the prime coordinate system will be the same as the lambdas I had obtained in the base coordinate system. Of course, it's the same physical quantity sigma that we're talking about. Although when you rotate your coordinate system or when you work in a rotated coordinate system, the components of the sigma will be different. So what we have found out is something very interesting. So let's summarize that by writing it. So any coordinate axis we choose, we get the same eigenvalues. So eigenvalues, lambdas, are independent of the coordinate system. They are a property purely of the physical quantity sigma. And we know that the quantity sigma denotes something physical from an application point of view. So its eigenvalues also denote or have some physical significance, and they should not be changing with the change of coordinate system. And that is what we have shown. So now that we have established the fact that the eigenvalues are coordinate independent, they are purely a property of the physical quantity sigma, let's figure out what they are. So at most, we can have 3 eigenvalues or 3 lambdas because we had a cubic equation in lambda. So we'll have at most 3 lambdas. So we'll call them lambda 1, lambda 2 and lambda 3. Remember these 1, 2 and 3, they are not indices as in the indicial notation. They are simply numbers which are used to denote the first, second and the third eigenvalues of sigma. And corresponding to each lambda, we will have an eigen direction because the equation we started with was sigma ij nj is lambda times ni. So when you multiply sigma with a unit vector n hat, you get lambda times the same vector. So if you substitute a lambda value, you will be able to get the corresponding n hat. So we have an n 1 hat corresponding to lambda 1. We have an n 2 hat corresponding to lambda 2 and an n 3 hat corresponding to lambda 3. In fact, you should see it in the reverse order that for a given vector n1 hat, if you multiply that with sigma, that is sigma ij n1j, you get a lambda times n1. So let's write it down. We can also write this as sigma ij minus lambda 1 time delta ij times n 1 j. This is equal to 0. So we call this equation A. Similarly, the equation B is for the second n hat. So if I analyze the equation number A in the matrix form, what this looks like is sigma 1 1 minus lambda 1 in this case, sigma 1 2, sigma 1 3, and so on. Now, of course, this matrix that we have here is singular, as we already discussed. So this equation has infinite solutions. So what that basically means is that this does not result in three independent equations, because we have three unknowns here, the three n components, because all sigmas and lambda 1 are known here as of now. So we need to calculate or evaluate the values of n11, n12, and n13. But we cannot use just this equation for that, because this matrix is singular. It has in fact a rank 2. So we need to find one more equation, and that other equation is the property that n is a unit vector. So we can use n1i, that is n dot n is equal to 1. So now using a1 and a2, we can evaluate the three n hat components. So now we'll discuss some cases, because when you're solving the equation, you will have some situations where all the situations will not be similar. So the first case is that all three lambdas are distinct. That is, the three lambda values are all different. So what this results in is three distinct n hat vectors. That is, n1 hat, n2 hat, and n3 hat are all different and distinct vectors. What's also interesting is that these three n hat vectors are mutually perpendicular to each other. So I'll underline that. And these mutually perpendicular n hat values, that is, these mutually perpendicular eigen or principal directions of sigma, they can form a right-handed coordinate system. Again, the fact that these three n hats are mutually perpendicular will be shown as a part of a problem later. For now, you can accept it as a fact. Let's discuss another case. So in this case, we have two roots of lambda cube equation, that is a characteristic equation, are repeating. That is, let's say in this case that lambda 1 equals lambda 2 and lambda 3 is different. So you have a repeated root in the cubic equation, the characteristic equation. So what happens here is that you find an n hat corresponding to the different lambda value. So we'll call it n hat 3 distinct. So let's draw this, hypothetically speaking. Let's say this is n3 hat. And then what we do is we draw a plane which is perpendicular to n3 hat. And now what you do is, for this same sigma for whose eigen values lambda 1, lambda 2, lambda 3 you've calculated, if you multiply that sigma with any vector in this plane that is perpendicular to n3 hat, you see that that direction is an eigen direction. So what I mean to say is that all vectors in this plane are eigen directions or principal directions of sigma. So since we will be interested later, as we'll see in the next lecture, to form this right-handed coordinate system using the three n hats, we will take any two mutually perpendicular vectors in this plane to form this right-handed coordinate system using the three eigen directions. We'll choose some vectors n1 hat and n2 hat. So this n1 hat, n2 hat and n3 hat, they form a right-handed coordinate system. But you must know the fact that all vectors in this plane that is perpendicular to n3 hat are eigen directions. So all vectors in the plane perpendicular to n3 hat are principal directions. So we choose any two perpendicular n hats in the plane to form our right-handed coordinate system of n hats. And I'll tell you the significance of doing that in the lecture later this week. So now that we have cases 1 and 2, so we'll have a case 3 as well. And case 3 is the case where all lambdas repeat. So all three roots repeat. That is lambda 1 equals lambda 2 equals lambda 3. So now you can guess that in this case all directions in the 3D system are eigendirections. Any n hat you choose in this case, you multiply that by sigma, you get this lambda, which is some quantity lambda naught times the same vector that you started with. So if you want to form a right-handed coordinate system using n hats, you can basically choose any three mutually perpendicular n hats in this 3D system. Just one more fact before we close the lecture, that if all the principal values of sigma ij, that is all the lambdas, are positive, we call the sigma, the tensor that we are evaluating, as positive definite. So sigma ij is called positive definite matrix or a positive definite tensor if all lambdas are greater than 0. And it's called positive semi-definite if lambda I is greater than equal to 0. I should write it this. If lambda I. So of course positive definiteness is more strict as compared to positive semi-definiteness, and a positive definite is always a positive semi-definite matrix. So in case you have one of the lambdas as 0, you would have a positive semi-definite if all the other lambdas are positive. So this brings us to the end of this lecture. Today we talked about the characteristic equation which is obtained by solving the eigenvalue problem, which is sigma times n equals lambda n. So you must now understand why we started talking about the idea of linear transform. So we have these special n hat directions which when multiplied to sigmas result in vectors which are in the same direction as n hats. These n hats are called eigen or principal directions. So we'll stop the lecture today, and in the next lecture we will be discussing more about these special eigen directions and doing tensor transformations in these coordinate axes which are formed by n hats. So thank you, and I will see you in the next lecture.